Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And let's see what interesting questions there are today. There's one from Leo here. Should we try to contact extraterrestrial beings by broadcasting signals into space, or is it too dangerous to reveal our location? I don't know how much I've talked about extraterrestrials and alien intelligence and so on. It's something I've thought quite a bit about, and I have to say my views have changed over time and have kind of stabilized at a point that is both interesting and not interesting. So when it comes to alien intelligence, there's sort of a question of what do we mean by intelligence? How special is it? And how alien is alien intelligence? So first question is, how special is intelligence? Well, I spent a lot of my life studying computation, systems that operate according to definite rules and perform operations. And when we ask sort of what's special about an intelligent system versus a merely computational system, one of the things that's been the result of a bunch of discoveries I've made over the last, 40 years or so, is that there doesn't seem to be a bright line of distinction between the intelligent and the merely computational. When we look at something like our brains operate according to definite physical, chemical, etc. laws, and the neurons are firing in this way and that way according to those laws. When we look at some process in physics, like, I don't know, the swirling air currents in the atmosphere, or we look at some process purely defined in a computer where one just has some simple rule and one just keeps running this rule over and over again. The question is, how do those processes compare in terms of sort of the computations that they're able to do? And there's this thing I call the principle of computational equivalence that says that in the end, the computations that get done in those different kinds of systems are actually equivalent in their sophistication. Of course, we think the ones that we do in our brains are much more exciting than the ones that the weather does or the ones that some computational system on our computer might do. But in a sense, the reason for that is that there's sort of an alignment of the things that we understand, the kind of narrative that we understand about how the world works and the things that are going on in our brains. And it's like, a quote people often say sort of is, the weather has a mind of its own. Well, yes, there are computational processes going on in the atmosphere that are quite as complicated as ones that go on in our minds or whatever else. It's just that those processes aren't aligned with the things that we sort of are familiar with as being sort of the thought processes of humans. So the way I like to think about this in terms of sort of our latest thinking is we have this thing we call the Roolead, which is this kind of entangled limit of all possible computations. And so all these different things, whether it's things happening in our brains, in the weather, in some simple computational system, they're all, in a sense, happening somewhere in the Roolead. And they're all, and in a sense, the question is, can we sort of move in the Roolead? Can we move from where we are in the Roolead, where the processes, the computational processes that we're familiar with our thoughts are in the Roolead, to where other kinds of computational processes are, and what kind of translation is involved in going from one to the other? Do we sort of, to what extent can we understand the mind of the weather, for example? Well, I think we can sort of have some assessment of distance in Rooleal space. So, for example, between two human minds will have different representations of information, different ways of thinking about things, but yet, with some approximation, one human mind can communicate with other human minds, as I try to do in these live streams. And the main way we do it is we use words, we use these kinds of sort of general concepts that are not specific to the particular representation of knowledge in my brain or in your brain. They're sort of transportable versions of those lumps of knowledge, so to speak. in sort of my life work of building our Wolfram language, computational language, the way I see what I'm doing is to invent these kind of concept lumps of computational work that are kind of transferable between, in that particular case, the human minds, human people using Wolfram language, and the computer implementing Wolfram language. So in a sense, I view kind of the content of Wolfram language, the structure of the language, as being an attempt to define something which allows you to move from the place in rulal space that we are as human minds to the place in rulal space that the computers that implement Wolfram language are. And in general, so, you know, between different human minds, there's some distance in rulal space. People who have sort of similar paradigmatic understandings of the world may be closer in rulal space than others, maybe easier to communicate with. When we get to things like, you know, pets and animals and so on, there's a certain amount of communication we can do. There's a certain alignment of our way of thinking about the world with the way that the cat thinks about the world, and we can sort of understand the emotional states of the cat to some extent by mapping them onto our own experiences of emotional states, and we can recognize that the wagging tail means something, and so on and so on and so on. Well, when we get further afield, when we get to the weather, for example, it's very hard for us to align our kind of way of thinking about things onto its way of computing things, or we could say thinking about things. So when it comes to thinking about alien intelligence, extraterrestrial intelligence, whatever else, it's sort of the same kind of thing. We can look at something happening in the universe, some pulsar that's rotating and generating radio signals that are very elaborate. And we can ask the question, is what it's doing a bit like a mind? Well, I think we can argue that at a sort of theoretical formal level, it is a bit like a mind. It's doing computations just like our mind does computations. The question is, can we kind of get inside what it's thinking? Can we align our kind of narrative for how things work with its way of thinking about things? Now, one thing to understand is science, the whole activity of natural science, is in a sense an attempt to communicate between the alien intelligence that is operating in nature and our human intelligence. Science is a way of taking the things we see happening in nature and trying to have a kind of narrative description of the things that we see happening in nature in such a way that we humans can kind of understand in some sense what's going on. So, you know, when we have our pulsar, it's doing its thing. Maybe the pulsar, we might imagine at an inner, there's a sort of the question, to the pulsar, does the pulsar seem like it's got this whole civilization, consciousness, and everything else going on? From the outside, we say, that's a pulsar. It does complicated things. We might use science to make a kind of conversion, a translation between the things that it's intrinsically doing and the things that we humans understand in our minds. But you know, one question we might ask is, does the pulsar have an inner sense of what it is doing? You know, we humans are convinced that we have an inner sense of what we're doing. That's kind of what that's our sort of notion of consciousness, is that we have this inner sense. I think that the inner sense is a feature. I think one of the things that's very important in that inner sense is that there is coherence to what we do. We have a thread of experience. We remember the past. We kind of have this thing where we believe that we're thinking definite thoughts at any given moment. That appearance of coherence is not a trivial thing. The brain has actual sort of mechanisms to try and keep our attention kind of focused in this one line that is kind of our thread of experience. It's not obvious when we think about the physical structure of us and our brains and how we fit into physics and so on, that there would be this kind of coherent thread of experience. I think that the fact is that at every moment in time in our modern theory of physics, we're made of different atoms of space. At every moment in time, the very structure of space, the structure of everything in space, is being recreated. It's being destroyed and recreated, maybe 10 to the 100 times per second, maybe more. It's continually being destroyed and recreated. Just like in this analogy I use quite a bit, you know, a vortex, an eddy in a fluid, it's it's made of molecules. As the eddy moves, it always keeps on getting made of different molecules, but yet we can say, look, there's an eddy and it's moving, and there's this thing that exists and continues to exist. So that's it's in that sense, we are these entities that, like the eddy, is continually made of different stuff underneath. Yet we have this idea that there's a coherent us that keeps on with this sort of single thread of experience, keeps on existing. And that's an important feature of having this notion of an inner self, so to speak, is this idea that there is this coherent thread of experience. And we can ask the question, you know, does the pulsar have that? From the outside, we might be able to tell it does, might be able to tell it doesn't. It's not obvious that that's a necessary feature of an intelligence-like thing. You know, it could be that humans, most of us sort of maintain a single thread of attention. You know, there are things which people might say, you know, that's a terrible psychiatric disaster if you're sort of having multiple threads of experience happening at the same time, because that's a very weird way to interact with the world. It's not something where there's necessarily good communication between another person and somebody who has multiple threads of experience happening at a time. But it's not obvious that the sort of the alien intelligence that's out there would have to be something which has a single thread of experience. Now, again, so what I'm basically saying is there's alien intelligence everywhere. The problem is it's pretty alien. And the idea that it is communicatable with is something, that's the difficult idea. How far away are we in Rullial space from the pulsar? Are we going to be able to use science to bridge things so that we can like understand what's going on in the pulsar or not? If we have that thing that we say, oh, it's an alien intelligence, that's a process going on this planet here, are we going to be able to bridge to understand so that we humans can understand, yes, we get it. Those things that we might think of as rocks or something, they're actually part of a civilization, and those are the great built structures of the civilization. They're the cities of that civilization are these collections of what might to us naively seem like rocks. So this question then of okay, so the question was asked here was, should we reveal our location to the aliens? Okay, interesting question. So what do we do? So let's say we beam radio signals out into the cosmos. We might say, well, okay, fine, but could be the case that that electromagnetic radiation going out into the cosmos has some effect somewhere. Probably won't have much effect, but let's say it does have some effect. Let's say that radiation, let's say a little bit of that radiation was beamed in the direction of, I don't know, the star Betelgeuse, big red giant star. It's which at some point in the next million years will probably go supernova. And somehow that radio signal, and I don't really know how this would work, but somehow that radio signal just hits that star just the right way so that it initiates some flow of magnetic gas or something, which somehow leads to the star imploding and going supernova, and there's a big bang. And I don't think it would do anything it's like 200 light years from Earth. I don't think it will do anything too terrible to the Earth. Although it might be a little exotic what happens with the sky being bright at night and things like this, but for a few days. But that's a case where you could say, well, we revealed our location. You know, maybe that beam of electromagnetic energy caused this magnetohydrodynamic process to be pointing in our direction. Maybe it released more energy in our direction. I don't know. It's a physics story. What I think one imagines is the more science fiction movie story of there was a signal and we sent out that radio signal, and then somebody came in a spacecraft and came and stomped on us. But I think it's worth realizing that story, it's sort of a continuous gradation from that story where you say it's a human-like thing that has intentions and is making empires and things like that, to it is a purely physical process, which by virtue of this, electromagnetic pulse that's going out from the Earth causes this to happen and that to happen, which causes some effect back on the Earth. Frankly, I think these effects are fairly tenuous, and I think mostly the universe, different parts of the universe kind of keep to themselves. Mostly the effect of something happening far away in the universe right now doesn't seem to be that great to us. We see starlight. Okay, that's fine. It's pretty small effect. We see gravitational radiation. We can see the merger of black holes. We can see it almost all the way across the universe. We can see that, but it's a tiny effect. It doesn't have an effect on our sort of everyday life. Now, having said that, I suppose, what effect do the stars have on our everyday life? This is a thing, back in Babylonian times, when astronomy and astrology were really one field, there was kind of this idea that originated at that time that, the configuration of stars has a direct effect on our everyday life. Most of the time, one doesn't believe that that's the case right now. One thinks, the stars, even the planets, don't have a direct effect on the things that we do in our everyday life. Now, of course, that would change if our technology was different. If we were routinely using the position of the planet Jupiter or something as for example, people at one time were thinking of using the moons of Jupiter as a navigation technique. And then it would start mattering to us. Where is Jupiter? Is it above the horizon? Is it not? Can I tell the time by looking at the configuration of the moons of Jupiter? Then you'd start to really care in a sort of everyday way about where Jupiter is, which we don't right now care about. Now, having said that, you can certainly imagine, the ancient, in times when there wasn't artificial light and so on, and it was really pretty dark at night. And what was there to look at? Well, there were the stars, and people would no doubt have put much more emphasis on the configuration of stars and so on. And this question of does the configuration of stars have an effect on life on Earth? Well, I don't know. And when, for example, a comet would come through, and you would see this kind of wandering star come in, and so I guess planets were called that too. But when you would see this sort of unusual comet arrive that you just hadn't seen before, people might have all kinds of conclusions about what that would mean for sort of for sort of everyday human life. But mostly the universe, the different parts of the universe have kept to themselves. So I suppose the question is, if we do something to specifically communicate that we're here, and that where we're not sort of keeping to ourselves as much as we might. Now, there are plenty of astrophysical phenomena, jets of particles that send huge amounts of radio energy in a particular direction, giant gamma ray bursts that go in a somewhat targeted way, and so on. There are plenty of phenomena astrophysically, even in other galaxies and so on, that deliver sort of signals in a particular direction. But I think mostly that hasn't had a big effect on the universe. So really the issue is there some alien intelligence that might be close enough in rulal space to us that we'd say, yeah, they're really coming to conquer us, they're making an empire, as opposed to just it's a cloud of gas and it extended across this, or it's an interstellar meteorite that came from here to there. The interstellar meteorite might have had some whole life story that we could start to tell in something that sounds narrative and human-like, but actually we might also say it's just a rock that happened to get thrown out of some exoplanet solar system and arrived here. So I think the philosophy of the question of sort of alien intelligence and the effect of revealing our location, it's a philosophically complicated issue, and I think it's one that I'm not really worried about the human-like empire builders showing up and deciding to colonize the Earth. That seems to me to be a tenuous kind of concern. I think there are things we might so at least pause for a moment to think about, like there are things that we can create with technology that have never been created since the beginning of the universe, so far as we know. I'm not sure that's really right, actually. I think that when people have said that particle accelerators can create energy densities that are as intense as happened at the beginning of the universe and haven't been created since. I bet that isn't true. I bet there are situations around black holes in various situations of high energy galaxies and things where, yes, you can absolutely create those kinds of energies. In fact, I'm pretty sure that's true because, among other things, cosmic rays, which are always bombarding the atmosphere, the Earth, mostly protons, mostly they come from the sun, but some of them come from much, much further away. Some of them come even from outside our galaxy. And the energies of some of those cosmic rays are incredibly high. Like the energy is such that if one of those cosmic ray protons were to hit me, now mostly it would just go through me and it produce a bunch of particles and then they would, but if that proton really stopped inside me, it would give me a big kick. And that's quite a remarkable thing for a single proton to be able to do. The highest energies that have been observed are around 100 joules or so, which is just a substantial amount of sort of mechanical energy, so to speak. Now, again, in actuality, when one of those particles, which are very rare in cosmic rays, goes through something, it doesn't all stop in the thing. So it doesn't transfer all its momentum to the thing that it initially interacts with. Instead, it produces a cascade of other particles and they get absorbed and further away, and eventually that momentum is transferred, but it doesn't immediately get so. But I think that there are, I guess I was saying that there are sort of this question of whether there are things we might be doing now that really haven't happened since the beginning of the universe. I sort of doubt it, given the presence of things like very high energy cosmic rays and so on. All right, another question here. There's a question here from Zayden. How to tell if something is natural or artificial? Yeah, an interesting question. It's a question that shows up in all kinds of places. It shows up in archaeology. Was this arrangement of stones natural or artificial? It shows up in something like, I don't know, when people are like scanning the ocean for a shipwreck. You got lots of rocks and other things in the ocean. What's the signature of something that was a human-made thing? Another example would be sort of captures on, is this a bot or is it an actual human behind it? Is it an artificial thing, or it's not really quite natural? That's sort of a simple rule-based thing that is a bot. I'm not sure that when you run a neural net and it produces some picture or it produces some chunk of text, do we think of that as natural or do we think of that as artificial? If artificial means there was a human intent somewhere in the middle of it, that's perhaps our operational definition. And that's what one tries to figure out. A website might try to figure out with a captcha, was there really a human in the loop here, or was this something purely automatic? I think this problem of how do you know if something is natural or artificial, a lot of the ways that one recognizes things as artificial have to do with simplicity. So, for example, when you see on the Earth a perfect straight line, you think, oh, that must be made by something, that must be an artificial thing, that must be a train line, that must be a causeway, that must be something sort of artificially made. On the other hand, when you see something complicated, you might say, oh, that must be a natural thing. It's a little bit screwy because we think of ourselves as, we're the great intelligent things on this planet. And yet the things that are most visibly artificial are the things that actually have simple geometries and things like that. Most of our technology also, we kind of recognize this is a technological thing, and we recognize it by virtue of kind of the simplicity of the structures in it, straight lines, circles, levers, cogs, things like this. And part of that recognition is historical. That is, we say, I've seen a cog before. Maybe somebody could have invented some kind of thing that's just some smooth surface that rubs against another one and so on. It doesn't look like a cog, and we wouldn't be able to say, oh my gosh, this thing is full of cogs. So it's partly the detailed history of human technology that's led us to have these sort of recognizable features. But it is something where, in a sense, it's a bit of an embarrassment that the things that look artificial are the things that are somehow simpler than the things we see in nature. You know, one of the examples I find fun is it's actually a quote from Immanuel Kant, a philosopher in the 1700s, who was said, you know, if you see a hexagon drawn on the ground, you know that it must have been intentionally created. Okay, well, turns out people have now found sort of cases where the pattern of flow of winds and convection cells and so on causes some sand to be arranged in hexagonal patterns. You see that in rocks. You see kind of Devil's Causeway type rocks where there are nice hexagonal kinds of rocks. These are things which indeed they were not. You know, Kant was wrong. They were not things that had a human-like intent to them. They were just things that happened as a matter of sort of natural processes. I think an extreme example of that is the North Pole, I think it is, of Saturn, has a giant storm visible through telescopes that's in a hexagonal shape. So these things where you think this is, you know, oh, we're going to have a hexagon, it's going to be a thing that we can recognize as being sort of human intentionally made, that doesn't really make the cut. You know, it's a kind of a fun thought experiment. Let's say in a future moment in civilization, we get to be sort of effective enough at doing things that we can move stars around in some pattern. What pattern would we put them in so that sort of the alien intelligences would recognize them as being a sign of an intelligence like us? I don't know. I mean, clearly, if you put sort of standard writing in something, then anybody who sees it, who is part of sort of our cultural thread, will say, oh yeah, I recognize that, that's a piece of English writing. Or even, I recognize that, that's writing. Now, you know, there may very well be things that are in cave paintings or things, you know, carved out of stone or whatever, which actually, to somebody at the time, not that they would have used those words to describe it, they would say, that's my writing. But to us today, it's like, that's just a bunch of scratches. I don't know what that is. Good example, sort of intermediate thing, is the quipus, that you find in Peru, these kind of things made of lots of strings with knots on them. I don't think anybody knows what those actually mean. Clearly they were done on purpose. Maybe they were an accounting system. Maybe they were just a generic way to record information. They were clearly, somebody actually made those knots. But what do they mean? And do they mean anything? I mean, could it be the case that people just made those knots decoratively, ornamentally, just because, oh, I don't just want straight strings, I want strings that have knots in them because they look nicer? You know, we don't really know. That thread of history has been broken, so we don't sort of have that cultural connection that allows us to know that. So that's some thoughts on that. Oh my. There's a question from Ark here. How far can an EMP from the human heart travel? So I think, well, EMP will be electromagnetic pulse. Usually you use that term to talk about huge electromagnetic pulses made by nuclear explosions in orbit and things like this. But one can, when the heart is an electrically driven thing, there are nerves that come from one's brain that are very well protected nerves in one's neck that are pulsing electrical signals to the heart to get it to beat. And you know, once it has that pulse, the heart is arranged so that if it's working correctly, so to speak, it just goes shtump and pumps blood and does all the right things. When the heart isn't working quite right, or worst case, when it fibrillates, and that means that it gets the signal perhaps to beat, but it doesn't operate in the way that it's supposed to operate, and it doesn't just have its sort of smooth beating motion. and start sort of flopping all over the place and not successfully pushing blood around. But the way hearts are set up, they have their structure is such that you just poke them and they tend to just go and do this pretty elaborate beating motion. It's a phenomenon, so-called attractor. So the very simplest kinds of attractors, you can think of in a mechanical system. It's just like you've got this whole landscape and you roll a ball and it rolls down to the lowest point, and that lowest point is kind of an attractor on the landscape. All these balls roll to that point. Or maybe you have a watershed where, on one side of the mountain range, the water is all flowing down to one side, the other side of the mountain range is all flowing down to the other side. That might be two different attractors. The heart is a more complicated kind of attractor that's a limit cycle attractor, that is something where when from lots of different kinds of ways it might get sort of stimulated, it ends up going into this state where it is always having this repetitive motion. I think the same kind of thing happens a little bit. It's slightly different, but a little bit like with a swing. You can, you sort of pump the swing, you do it in all kinds of different ways, but in the end, it's going to swing back and forth at a certain frequency, and that's sort of the thing that you're going to get to. Okay, so anyway, hearts have this electrical pulse. They also have they have lots of electrical activity associated with actually I'm now well okay so there's electrical activity that is what you detect when you do an EKG, and when you do an EKG you put electrodes on different places on your body, and the electrical signals are going from your heart, from the junction between nerves and muscles in the heart, and they're going and you're detecting those, and you're detecting them by having different locations on your body. You're able to detect different parts of the cycle that corresponds to heartbeats. And so you'll have I don't know this stuff too well, but you'd have what is it, the QRS interval. There are different parts of a heartbeat that show up as different pieces of the pulses that correspond to EKG, electroencephalography, and electrocardiography. Electroencephalography is for brain waves. And I think the K is because it was originally in German, if I remember correctly. And strangely, there's the whole development of EKG happened in the early 1900s. It was a pretty early application of kind of radio-ish type things, and also of amplifiers, the ability to amplify small electrical signals. And there's sort of there's a lot of kind of both folklore and what later became science. It was also a place where sort of AI in medicine came very early. I think it must have been maybe the 1970s. Certainly by the 1980s, there was automatic interpretive EKG, where you would have some, you'd have an EKG signal, and it's just a bunch of wiggles, but it could tell you, that's a normal rhythm, or that's abnormal, that corresponds to some kind of arrhythmia, that corresponds to this or that. It was a very early place where kind of AI came into medicine and became a very standard thing, as a thing that could automatically be done. Okay, but the question here is, when you have these electrical signals, normally you have electrodes, you stick them on. They have sticky stuff on them, and there's a little piece of metal in the electrode, and you're actually touching the electrode against your skin, and you are a conductor of electricity. You have enough. You have a human body it's not a great conductor of electricity. It's not like a copper wire or something, but we're an okay conductor of electricity, which is kind of a good. It has various good effects, but it also has the effect. I mean, I should explain. Nerves are sort of efficient conductors of electricity, but also just general tissue is also a conductor of electricity in the same way that seawater is a conductor of electricity, and for the same kinds of reasons. It's this kind of ionic, salty thing that we're kind of made of that conducts electricity. So when we can connect an electrode from an EKG device to us, where we physically have a metal electrode that then goes to, sends the electricity on a wire, and we're physically connecting to our skin, and that's sort of connected to the bag of salt water that is us, and we're able to find electrical signals that way. Now, so if we say out from us, if we're like away from us, how do we detect? Can we detect the electrical signal from a heart, for example? My guess is that with a sufficiently sensitive detector, yes. And one of the features of sensors is they always get better. It's been a progression, that has been going on for at least 140 years or so, since the early invention of amplifiers and so on. We've been progressively getting more and more and more sensitive sensors. There's kind of a whole concept nowadays of quantum sensors, where you're trying to sense the effect on single electrons, single atoms, things like that, as a way to detect very sensitively, for example, magnetic fields. So I don't know if the heart produces significant magnetic fields. It must produce some, because whenever there's sort of moving electrical charges, you get magnetic fields. For example, in the brain, where we got all these neurons that are firing and having little electrical pulses, there also are magnetic pulses there. And there is a mechanism for doing magnetic MEG, magnetic encephalography, which was popular 25 years ago. I haven't heard about it much recently, where you are able to detect magnetic sort of emanations from the brain. My guess is the same thing could be done for the heart, although I've never heard of it being done. One can expect that sort of eventually from a distance, you should be able to detect those things. Now, the problem with MEG, for example, is I know back 25 years ago or so now, people had a lot of trouble because you had to be in this incredibly electrically quiet environment where there are no, buzzing fluorescent light bulbs. There are no, there's no mains electricity with all kinds of electromagnetic signals there. You had to be in this very electromagnetically quiet environment to be able to detect these incredibly small signals. And so that's a challenge, but I have to say that those kinds of challenges, again, when there's a background noise to a signal, again, the world of signal processing communications has shown over and over again that by cleverness, engineering cleverness, you get to sort of have, let's say, the detector that's measuring the ambient noise, and then that's comparing it with the actual signal you're trying to measure, and being able to sort of cancel out, sort of echo canceling, noise canceling, headphones and things are trying to do exactly that with that type of thing, where they're sort of sensing the ambient and then getting rid of it for the signal. So I think my guess is that in principle, you should be able to have sort of detect heartbeats at a distance. Now, as a practical matter, there are much easier ways to do that. If you just want to detect the heartbeat, you don't want to measure all these electrical signals associated with the heart. Whenever blood pumps through us every second or so, when every heartbeat, oxygenated blood is redder in color than unoxygenated blood. When blood is coming from the heart, it's when it's being pumped out, it's the lungs have put oxygen into the blood, and when it's pumped out, that will be oxygenated blood that's being pumped out, and it's somewhat redder than the blood that comes back in to the heart after that. Then that oxygen gets dumped in our tissues all over our bodies to be part of allowing us to metabolize and so on in different to have energy for our cells in different parts of our bodies. And so that there's slightly redder blood that's going out than the blood that's coming back in. And so that means that every part of us every second is slightly redder than it is in the off time, so to speak. And so a few years ago, people had made, even with traditional cameras, like probably the ones looking at me right now, you could probably measure my heart rate by looking in precise detail at the video frames and saying, yes, that frame, I'm slightly redder than I was in that frame. it's a small effect, but it's an effect you can measure. And that's so from a distance, you can measure heart rates that way. Although for some reason there was popularity in doing that about 5 years ago, but it sort of died off. I think that it is hard, if you have an infrared camera, a camera that is looking not at visible light, but at the sort of end of this, at electromagnetic radiation that more corresponds to radiant heat. That's a place where you might be able to see even more of this kind of that's a different effect. You'd be seeing you could be seeing different different parts of maybe that's probably a different. I don't actually know whether probably is the case that when you pump the blood in through, when the blood is sort of pumped out, it gets slightly hotter. Maybe I'm not sure actually, not sure. I mean, I know that with infrared, there's always the question of, for example, if you stick a thermometer in your ear, that's a bolometer. And what it's doing is it's measuring infrared radiation from your eardrum. It's different from if you stick a thermometer in your mouth, for example. Well, the old-fashioned thermometers had mercury in them, and the mercury expanded depending on your temperature. And so you'd see the mercury would go further up the tube of the thermometer if you had a higher temperature. Nowadays, the thermometers you stick in your mouth are electrical, and they work by the fact that the resistance to electrons going through a metal changes with the temperature of the metal. Let's see, how does it go? I think the higher the temperature, the more the atoms in the metal are jiggling around, and the more difficult it is for the electron to make its way through the metal. So the more resistance there is to the electron, and you can detect that, and you can detect the change of that resistance as you change your temperature. When you stick the thermometer in your mouth, the thermometer comes to equilibrium, gets to be the same temperature as that pocket of heat at the back of your tongue or whatever, and that's how that works. But the thermometers that you stick in your ear, they are just looking at infrared radiation coming from your eardrum, and your eardrum has lots of blood flow in it, and it's something that will be sort of more or less your core internal temperature, and it's then seeing how much infrared light comes from that and trying to measure that. From a distance, you could say, and people set these up in, well, both before COVID and during COVID, as is somebody sick or not? Look at what their temperature is just from a distance from some infrared camera. That turns out to be pretty difficult. I mean, because the temperature of the surface of one's skin is not necessarily that closely related to the temperature that one is internally, so to speak, because out at one's skin, one's exposed to the air, which is at whatever temperature it's at, 70 degrees Fahrenheit or something. Deep inside one might be at 98.6 degrees Fahrenheit, but that's by the time you're looking at the outer surface, it's much harder to detect what the core temperature is. You have to make various corrections. It's not clear that works right. It's you can have the person who has the colder handshake and the warmer handshake and so on, and they might both have the same internal body temperature. Just a difference of the way that capillaries and so on are delivering heat to the extremities of the body and so on. Let's see. Oh my, there's a comment from L3 maybe. If I'm in an object moving at 2/3 of the speed of light, moving towards another object that's moving at 2/3 of the speed of light, what would the object look like to me while on the first object? So, okay, what happens when you go close to the speed of light? First point is, the only way we get to see things is by photons of light, which go at the speed of light, coming to our eyes. Okay, the big thing that sort of launched relativity in 1905 was the following surprising observation, that sort of however fast you're going, the speed of light always seems to be the same. So that means that you might think, oh, if I'm running really fast and I have a flashlight, that if I'm running at half the speed of light and I'm shining my flashlight out, the photons coming out of my flashlight will be going at 1.5 times the speed of light, because they got half the speed of light just by me running and another speed of light by them sort of being made as photons in the flashlight. So they should be going at 1.5 times the speed of light. Okay, so the big observation, which came out of Maxwell's equations for electromagnetism, which had this property, is that the speed of light doesn't work that way. The speed of light is always the speed of light, however fast you're going. And so what Einstein figured out in 1905 was, how could that possibly be right? How could you possibly have it be the case that the speed of light is constant independent of your state of motion? Well, the way you can have that be that way is if actually length and time change when you're in motion to sort of compensate for the fact that the speed of light is staying constant. So there are two big effects. One is time dilation, the other is length contraction. So time dilation says the faster you go, the slower time, your time will seem to be going relative to the time of somebody who is staying at rest. So that means if you have a clock and it ticks every second, and you think it ticks every second, the person who's at rest will see, and you're going really fast, and they pay attention to what's happening to your clock, they'll say, no, it's not ticking every second, it's ticking every 5 seconds or something. There's a formula. The formula is the rate at which the clock ticks will decrease by a factor of 1 over the square root of 1 minus v squared, where v is your velocity, divided by c squared, where c is the speed of light. So it's 1 over the square root of 1 minus v squared over c squared. Okay, so that's the formula for time dilation. It's also the formula for length contraction. Lengths get foreshortened by when you're traveling fast. So if you sort of see something whizzing by, it will seem to be shorter than it would be if it was at rest. By the way, in our physics project, we finally get to understand at an intuitive level how time dilation works. I mean, in other words, in the way that one describes time dilation and what I just told you, it's kind of just a consistency condition. Because the speed of light appears to be constant, therefore there must be time dilation. That's how the speed of light manages to maintain its constancy. In our physics project, we think about things this way. So you've got an object, and well, in our physics project, everything is computing all the time. The progress of time is the process of the universe computing its next state, its next state, its next state. That progression of computation is the progress of time, is the progression of time. Well, motion is about an object that's here getting reformed somewhere else. And when that object reforms itself, it has to do all kinds of computation to take the sort of atoms of space that represented it here and make there be atoms of space over here that represents the thing. So here's what happens. When the thing is just sitting still, it has to compute what's going to happen to it next. The progress of time is this computation. So that computation runs at a certain rate. Let's say that the object is also moving. Well, it's going to use some of the computation that it can do to reform itself at a different place in space. It's going to basically use up some computation in doing motion. So it has less computation to spend to update its own internal state. So in a sense, that's why time dilation happens. At rest, all of the computation effort can be used to just update the internal state of the object. When the thing is in motion, some of the computation of that gets used up in reforming the object to different places to execute the motion. And so less computation is available to update the object itself. And so that means that effectively time is running slower because there's less computation available to do that time updating. Okay, but in any case, the two big effects, length contraction and time dilation, two big effects in relativity. So there's another effect as well. When an object is going away from you, it gets redshifted. In other words, the frequency of light, the photon that comes from that object, essentially, because the object is going away from you, the photon, the wave fronts are being pulled apart, and that causes a light to be shifted in the red direction in the spectrum. Red goes to lower energy, longer wavelength. When an object is going away from you, that's what happens. For example, distant galaxies, the frequency of light that comes from them, the furthest away galaxies, the frequency of light is a factor of 2.5 times smaller. The wavelength is 2.5 times larger than it would be for a galaxy right next door to us. And for the most distant objects we see in the universe, things like quasars, there's a factor of 5 difference in frequency. So it can be a big effect when things are going effectively receding from you at a significant fraction of the speed of light. When you get the reason, in a sense, if you try and accelerate something like in a particle accelerator, try and make it go faster, 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 keep going to the speed of light. That same formula, 1/1 square root of 1 minus v squared over c squared, is also, in addition to length contraction, time dilation, there's also an increase of mass of an object. And so as you go close to the speed of light, the effective mass of an object increases. So if you're putting force on the object to accelerate it, force is equal to mass times acceleration. So the acceleration is, if you have a constant force, the acceleration is the force divided by the mass. But in relativity, there's a correction factor to that because the effective mass goes up as the speed goes up. So as you try and get something to go at the speed of light, it becomes more and more and more difficult to get the thing to go very close to the speed of light. And that's why it's it gets infinitely difficult to make something actually go at the speed of light. For massless particles with no mass, like photons, they just go at the speed of light all the time. But for anything with mass, the effective mass just goes, but gets higher and higher and higher as you get close to the speed of light. You have to push harder and harder and harder to get that last, 99.999% of the speed of light. Okay, so the question is, the question that was asked here was about objects moving close to the speed of light. Objects distort in really weird ways as you move close to the speed of light. For example, actually, there's a chap who was a student at our summer camp who wrote a nice article on kind of all the different things, how you really think about the appearance of objects, large objects, as you go close to the speed of light. But a lot of very weird things happen. I'm trying to remember some of the effects. I mean, a cube, for example, twists. If you have a cube going fast, because you have to think about the front of light coming from different parts of the object. It's actually a fairly complicated transformation. That is, light is coming from these different parts of the object. You're deforming the wavefronts of light. You're getting often a strangely distorted appearance of the object. Things get elongated, things get shrunk. It's kind of complicated, and things change color because when it's going away from you fast, it gets red shifted. Coming towards you, it gets blue shifted, and so on. So let's see. So I mean, there's a lot of tricky things here. I mean, like for example, there's so many sort of paradoxes of relativity that happen when you start trying to think about large material objects. So, for example, a famous one is you're running through a barn and you have a big pole, and the pole is much longer than the barn, but you're running so fast that there's length contraction on the pole. So is there a moment at which somebody can close the entry door and the exit door from the barn, and you're in the barn just for that moment, and because you're going so fast, your pole is foreshortened and it fits in the barn? Well, it's more complicated than that, because you have to start thinking about the way that the signal to open the door, close the door, how fast those signals propagate. Do you know when you're going to be in the barn? Do you have to predict that, or do you have to send a signal once you're in the barn, and so on? There's another one of these. There's a whole collection of these sort of pseudo paradoxes. There's another one where you have two rockets that are sort of identically programmed to fire their rocket thrusters, and they have a string between them. And eventually the rockets, if they're going sufficiently fast, will be foreshortened by length contraction. But then the question is, does the string break or not? And again, it's a complicated question of what the timing is about one rocket versus the other, and when things happened and so on, that determines that. So it's fairly complicated, and it's I would say that I think I have had decent but not perfect intuition about what sort of material objects, but big things look like if they're going close to the speed of light. All right, I should wrap up soon here, but maybe one or two more questions I can try. Okay, there's a question from Riveting. Dogs cannot understand mathematics, so we think. Similarly, humans must be limited in their ability to grasp aspects of reality. Is our ability to understand upgradable? Would biological evolution with better brains or merging with AI allow us to break through biology's limitations and become new dogs who can understand mathematics? That's a very interesting question. In a sense, every time we get new technological devices, new instruments, when we have an infrared camera, we can see things that were previously unseeable to us. When we have microscopes, we can see things that were previously unseeable to us. So in a sense, the development of technology is a story of us extending our ability to understand the world. The same is true with science. As we invent new paradigms for thinking about science, we expand our ability to understand the world. In terms of this Rouliad concept that I talk about, we're gradually expanding in Roulial space. We're gradually encompassing more different kinds of ways to understand the universe. So I think the answer is we already have a decent amount of experience in sort of seeing the expansion of our sensory capabilities through these different kinds of technological devices. Now the question is, do we get to provide a narrative description, a human understandable description of what's going on? That's an interesting challenge. Now, sometimes we've succeeded in doing that. We can describe things we see through microscopes. We say we didn't at first, we didn't know what we were seeing through microscopes or through telescopes. We had no idea. But then we started to say, that's a galaxy. That's a nova that happened, this kind of thing. We have descriptive terms that allow us to talk about things that were initially, distant from our everyday experience. So I think the same thing is true of lots of, as we extend our sort of capability for noticing things in the world, we get to have different kinds of descriptive terms. Now, for example, one area is even in infrared vision, we don't have great, how would we present something which is visible light plus infrared? Or with visible light, our particular sensory system senses red, green, and blue, but, we could sense 100 different frequencies of light. The mantis shrimp, I think, famously senses maybe 15 different frequency bands. But we could sense all these different frequency bands. It might be quite interesting because, based on, we say, I recognize that thing. It looks like copper. It's copper colored. Well, we can pick that up by noticing that copper has this characteristic color that we sample from the red, green, blue parts of the spectrum. But if we had hyperspectral imaging, where we're looking at the whole range of different frequencies, we might be able to just look at this thing, which to us just says, oh, it looks like a white powder. But with hyperspectral imaging, we might be able to say, no, that's calcium carbonate or something. We can immediately tell that just by virtue of this detailed spectrum that we can sort of hyperspectrally see. But one of the questions is, let's say we're going to present this as a technological device, and it is a near-term issue because hyperspectral imaging is technically possible. The devices are still somewhat expensive, but they're coming down in price. But we can make a hyperspectral imaging device. We can even do that with a traditional camera, like a standard webcam-ish type camera, phone camera or something. The way a phone camera works is it's got these little sensors, essentially transistors, that are sensing well, actually more like photodiodes, but that are sensing kind of light falling on different parts of this of the array that represents sort of the retina of the camera. And the way it senses different colors is there's a mask, and that mask has sort of a red filter, a green filter, a blue filter, and so if that particular pixel was got an electrical signal, that means the light got through the red filter, and that means it's red light and it hit that part. Another part is green light, it hit that part. Okay, so it's technically quite easy to say, well, let's, in addition to red, green, and blue filters, let's put a whole bunch of other filters there so that we're able to sense, we're able to detect when there's the light of other frequencies. You can do the same kind of thing with infrared. It's more complicated because lenses and things don't work the same way for infrared, same with ultraviolet and so on. Actually, existing lens systems and even the sensor arrays are capable of sensing somewhat into the ultraviolet, I think, usually. But it depends on those filters, whether they actually get to detect ultraviolet light. And normally we don't think that's useful because that's not what, when you take a photograph with your phone, and if you take a photograph of your cat with your phone and your phone was seeing ultraviolet light as well as seeing ordinary human light, your cat might have a lot of weird features. You'd say, that's not my cat. That's something, that's a weird ghost cat or something, and not very useful. So that's not really done right now. But it's certainly possible to have hyperspectral kinds of imaging, even with fairly traditional technology. So then the question is, let's say you've got a hyperspectral image of your cat or of whatever it is. How would we display that to us? Because our current sensory apparatus only deals with RGB. So we'd have to kind of make sort of false color things. We'd have to make captions. It's not really clear how to do it. It's an interesting question, how one should best do it. And it's something which would be nice to solve because it's actually a near-term technical possibility if we had a good way to do it. So that's an example of, we've got the technology in that case to sense things beyond our normal sort of, range of vision. But now the question is, how do we present that into our brains? And the answer is that if we have some good user experience, some good way of some good visualization technique or something, we'll presumably learn, oh, that's what that means. Just as, when writing was invented or something, it's like that was a bunch of squiggles. Well, no, we learn what it means. We learn kind of we learn something which makes it significant to us. So I would expect the same thing would happen if we had some way of presenting kind of these hyperspectral images. And that's a way that we're kind of extending our sort of domain of capability. Now, your average dog, your average dolphin, it has senses we don't have, or at least we don't have as good versions of them. Dogs have good senses of smell. Dolphins presumably have senses of fluid motion and things like that. If the dog could be telling us, if we could attach a dog nose to us, what would we do with the results from that dog nose? Let's say we could have a lovely display of kind of, the smell landscape from the dog nose, from the artificial dog nose. And by the way, artificial noses are a thing that have been slowly coming into existence as sort of chemical detection technology gets better and so on. But so we've got our artificial dog nose, and then we're trying to interpret, what does it mean? And maybe, again, we'd have lovely visualizations where you've got this purple piece coming in from here, and that's a sugary smell, and we've got some other thing coming in from there, and it's a different color. But yeah, I mean, we have to then learn sort of how do we relate to that? How do we get familiar with kind of the idea that when you see a purple piece in this place, it probably means this is going to happen. We are pretty good at learning all kinds of things about, oh, this is what you see, so this is going to happen. That's what a lot of experience and training of lots of kinds says. When you see this, this is going to happen. That's what we're also trying to capture in machine learning when we train, when you see this example, this is what's going to happen. And, in lots of domains, there's increasing success in doing that. And that, in a sense, could be used as a pre-filter for, the artificial dog nose. It's got a neural net and, running behind it, which sort of says, in certain cases, it says danger, danger, killer locust or something, attack. I don't know what that's not a good example, but chemical leak, harmful chemical leak detected or something like this. And that's something which is sort of an overlay on top of the raw data that you might otherwise be able to detect by saying, oh, I know when there's a purple and a green thing there, that corresponds to methane and, whatever else. I think that's my thinking about that. And what will we learn about the world when we have more sensory modalities? Probably a lot. Biology was launched by having microscopes, astronomy by having, and a lot of physics by having telescopes. I think a lot of modern physics and quantum mechanics probably launched by having electronic amplifiers. The things we learn in modern molecular biology from having the ability to do sequencing and things like this, and to understand, how a protein is constructed, those kinds of things. Whenever we have these new detection methodologies, there's an awful lot more we can understand about the world. And once we understand it about the world, we have the potential to sort of build our world based on that understanding. We have the potential to do microscopic things because we've understood stuff about the microscopic world by using microscopes. So yes, I think that is the story, in a sense, of the progress of technology and of science, that we gradually get to expand our domain of both understanding of the world, sensing of the world, and making the world do things that we care about, so to speak. And, to be able to even give an account of what it would be like if we had that connected dog nose or hyperspectral imaging thing, it's very difficult. It's something that I sort of kind of like to mention to science fiction writer friends of mine as something, try and make something which is sort of a description of kind of what it's like to have very different sensory modalities from our own. It's really hard. I was thinking about this just recently, and I'm like, how do you describe this? We don't have words that describe it. I mean, it's challenging enough in things that are concepts and sort of the theory of multi-computation that I've been trying to develop and so on. We don't have words for these things. You have to invent words. And, there's only a certain rate at which you can invent new words. If you wheel in a boatload of concepts and you say, I'm going to tell you 100 new words, good luck. People are not going to understand them. There's a certain slow rate at which you can sort of inject things into kind of our general cultural consciousness and have people understand those things. I mean, this is sort of, in a sense, the story of a lot of things I've done in my life of trying to develop new things, computational language, Wolfram language, and so on. A lot of things in science, one introduces things where necessarily one is pulling in a lot of new concepts. And to explain those concepts is often quite challenging. And often sort of the anchor moment is when you invent a word for that concept. And now you start being able to talk about it. The Roolead, for example, we got a word for it. Now we can start talking about it. Eames, the atoms of existence. We've got a word for them. And just yesterday, there's a new kind of version of an atom of existence. Atoms of existence have an identity, but nothing else. And whenever sort of, it isn't the case that you get two copies of the same atom of existence. These Eames, these atoms of existence, I'm thinking, an alternative to the word Eam, which I rather like, would have been something like AOE, because that's atom of existence. But I don't know how you would pronounce AOE, so it's not a winner. But in any case, Eames are unique. But yet we had a notion of something which is kind of like an Eam, but it's more like a variable in a programming language or a mathematical variable. It's just an X, and it's sort of an arbitrarily chosen thing, but it's the same every time it appears. We need a name for that. Once we have a name, we'll be able to start talking about it and understanding it. But that's kind of the challenge, is how do you take, and in a sense, that's my challenge, my sort of life work is mostly about creating our computational language to describe the world. And really, that is a story of how do you take sort of the complexity of the world and gradually find these kind of concepts that you can name, that you can piece together to talk about the aspects of the world that we care about. Memes here is commenting that smellography is an emerging field, which I've never heard of. I have to go look that up. Harry is commenting that I think with respect to hyperspectral imaging, no problem, the brain would just incorporate new frequencies and we would see it like a new color. I don't think so. I don't think so. You say, what color is that? Well, we've got our description. We've got our color triangle. We've got our red, green, blue sort of color space. Something else is really something else. And it's something where it's like, I have no word to describe that. I am seeing something where I have no word to describe it. One of the things that's been interesting in my life, I've studied quite a lot simple programs in the computational universe. And regularly when I do that, I was just doing that last night, actually. I was studying a bunch of programs, never looked at before. And it's like, wow, these things do a lot of complicated stuff. What do they do? Could I tell somebody what they do? I have no words to describe this. You can see the picture, and it's like, this is doing something really funky, but I don't have a word to describe this. I don't have a way of taking the complexity that I'm seeing and reducing it to just saying, there's a word that describes this, and that word is sort of a robust concept that I can communicate to somebody else. I don't have that. Now, if I saw enough of those kinds of patterns, I would make up a word. For example, many years ago, I had this idea with cellular automata, these simple programs, of classifying them into these 4 classes of behavior. And so now anybody who's in that biz would say, if I say a class 3 cellular automaton, they've immediately got an idea what that means. A class 4 cellular automaton, they've got an idea what that means. So again, that was sort of making something like a word that classifies a very big bucket of behavior. A little bit like, you might say of a material, oh, that's a solid, oh, that's a liquid, things like this. Anyway, it's yeah. Okay, one more thing, then I wouldn't really need to wrap up. I'm getting reminded here that I'm late for something else. There's a comment here from RBS. When we perceive things in 3D, how does that work? Is it that we're like seeing different colors in different eyes? No, the main way we, okay, so there's this old technology, 100 years old, I think, where you can put a red filter over one eye, a green filter over the other eye, and and then you can look at an image, and that image will seem like it has depth. The way that we see depth, we perceive depth in our eyes, is that we've got 2 eyes, and we're seeing things from slightly different angles. Something that is a few feet away, there is a certain difference of angles of what we're seeing. We're seeing one side of the thing when we have from our left eye and one side of the thing from our right eye. When the thing is close to us, there's a much bigger disparity. There's a much bigger difference between what we see out of our left eye and what we see out of our right eye. When the thing is a long way away, there's only a tiny difference of angle between seeing from our left eye and seeing our right eye. And so the images are much closer together. And our brain and our visual cortex at the back of our heads has a pretty good way of comparing the images from the left and right eyes. There are nerve fibers that kind of get mixed up from the left eye and the right eye. And there's this sort of comparison that's happening in our brains where we say, how much difference is there between that part of the image, between the left eye and the right eye? And so that's how we sense depth. That's how we tell how far away something is. And that's a good example, actually, of a level of perception that is beyond sort of color and things like that. That's a pretty subtle level of perception that we are getting in those nerve fibers in our brains that comes from sort of this fact that we have 2 eyes and we're looking at things from 2 different angles. I mean, if we were an insect or something that has this compound eye with, hundreds of different little eye pieces, we'd have to integrate that in a different way. We'd have a very different experience of vision. But so the way that mostly the way we see depth is by this comparison between our 2 eyes. Now, it's not the only way we see depth, because even in a photograph, you can say, there's perspective, there's this thing which looks like a crater or looks like a hill, and it has shadows on it, and we're seeing depth that way. We also get cues about depth from things like shadows and shapes in general. And when there are now machine learning systems that will guess the 3D structure of an image just from its 2D structure. In fact, that's used sometimes to make a movie that was originally a 2D movie and sort of make it 3D without having had 2 cameras photographing the whole movie, is by using this kind of fact that, one kind of knows that this thing is that shape. And so for example, when there are multiple frames in a movie, you can kind of see between the different frames in the movie, you're kind of going around the same object. And so you get a sense of its 3D shape. I have to say that 3D movies have not been as popular as people have thought multiple times in history they would be. And so that technology, I don't think has gone as far as it might have done. But yeah, the way that we sense distance is by this comparison of what we see out of our left eye and our right eye. That's the primary way, but also just by knowing what things look like. And sometimes we get confused. There are kind of optical illusions and things like the standard illusion where you say, is it a crater or is it a hill, based on this sort of circle, and then you've got this kind of this piece that makes a shadow, and sometimes it even will pop between one and the other as your brain kind of says, I think it's that, and so on. So that's how that works. And I think by the way, when it comes to sensing depth, there's a big cheat that's used by your average cell phone these days, and it's also used by 3D scanners, which is this approach. It's called structured light. And so what happens is your phone, for example, projects a grid of infrared light onto your face, for example. And by seeing where that grid, if your face was flat and that grid was projected in the right way, it would just be a straight grid on your face. But if your face isn't flat, that grid will be distorted. That grid, as seen by the camera, will be distorted by the fact that some parts of that grid were falling on something which was further away than others. And so a lot of, when you're doing 3D scans with a phone, for example, or when it's doing face recognition, for example, it's typically using, the shape of your head is detected by looking at the distortion to the structured light, to this array, this grid of infrared light that's projected on your face. And that's sort of the big cheat that we humans don't get to use. We don't have an infrared thing that's sort of detecting 3D structure. Another example of this is LiDAR. In sort of the fanciest self-driving cars have these things. Usually these days, there's still this sort of donut-shaped thing on top of the car, which has a big spinning thing inside it that is using infrared light again to detect. That's more sort of detecting how long it takes for a signal to come back reflected from something and able to form a 3D map of the environment that way. And that's what one does for sort of the fanciest 3D, fanciest autonomous car technology. There are other cars like Teslas use just cameras, and they're having to use the technology that's much more like the way humans do it, of both. And I don't think they're using. No, I don't think they use structured light. I think they're just using pure camera images, and they're using differences of images from two different cameras, and they're using sort of the progression of the image over time and things like that to be able to sense 3D structure. They have typically have a nice kind of display that shows you the reconstructed 3D image in real time, and you can see that some of it is quite accurate, and some of it just goofs completely, and some of it is like, yes, it recognizes there's a van there, there's a car there, there's a person there, there's a bicycle there. And I do kind of wonder, I haven't had a chance to try this in an exotic location where there are all kinds of safari animals running around. I don't know what it thinks some of those things are. I would be curious to know. And that's a sort of situation a little bit like the situation with humans, where we're presented with something which is just very different from our common experience. And it's like, what is that thing? Do we have a description of it? In looking at sort of this computational universe of possible programs, that's a really common thing to see something, what is that thing? How would we describe it? All right, I should wrap up here for today. Thanks for lots of interesting questions. And I see there are many saved up, but I'll also try and address new ones. I think I may miss next week, but should be back with you all soon on another live stream. And I do remind people, if you are curious about other topics, I have now done, what is it, maybe 100 of these. Is that right? Sounds about right. And they are pretty nicely archived together with word clouds of the topics and text of questions and so on. And so probably searchable, and you can find what goofy things I've said about all kinds of different topics. Anyway, thanks for joining me this time, and see you another time. And bye for now.